Assalamualaikum students, welcome back to my channel Chemmuneeb. So we shall start from where we left in our previous video of Feb March 2025, paper 42, chemistry 9701. Before going into the explanation of the questions, you can have a look into the previous part of the same paper, which is shown over here on the screen. And you can also go through other papers of the N9701, especially for those who are giving the composite exam. You can find multiple past papers solved by me on this YouTube channel. And don't forget to subscribe my channel. Now, moving to our past papers, continuing from the question number 3, and we had the part B, subpart 3, use information in table 3.2 to calculate the value of equilibrium constant Kc for this reaction. So we are supposed to find the Kc value. So now, for this purpose, we have to first construct the Kc equation for this chemical reaction, Kc expression. So we know that Kc is basically the concentration of the reactants divided products divided by concentration of the reactants. So here the products will only include this complex and the reactant will include only this complex, because we are not provided any information regarding the ligands of polaridine and the thiocyanide ion. So we'll not include those ones in the expression. So product will include concentration of iron with 5 water ligands. Tetra, we call it as penta aqua. This is penta aqua. Or you can also write as hydroxo, pentahydroxo, and have 2 plus divided by the concentration of the reactant complex, which is Fe 5 water ligands and SCN ligand 2 plus. Now we'll apply the values from the table given. From the table, we see that the value for the one containing fluoride or fluoride ligand is 2.40, and the complex containing a thiocyanide ion ligand contains 1.40 times power 2. So we'll apply these values over here. We should have 2.40 into 10 raised to power 5 for the fluoride ligand. And for the thiocyanide, it is 1.40 into 10 raised to power 2. So then the value shall come out to be 1714. Although the answer on the calculator will give you 1714.23, but we have to reduce the value up to the minimum of 4 significant figures here. The reason is that the values provided in the table includes 2 significant figures here and 2 significant figures here. So that's why we have to take only the values other than the decimal point. So we have only 1714. Now the next question, a few drops of KFR added to solution this of aqua followed by a few drops of KCl. Use combination table to describe any observation after each addition. Now in this question, we have to consider the table here. So what we observe in the table, it can be clearly seen that we are going to add the Kf into the tet hexa aqua iron complex. Now, when we add Kf, we are basically adding the fluoride ion here, which is the ligand acting over here. So basically, this should form the FeH2 5. So 5 water ligand with 1 fluoride ligand. So addition of Kf into this compound, I can write like this, that I'm going to react the FeH2O6 complex with Kf, then I would get the formation of Fe5 water ligands and a fluoride ligand. And the charge on it is 2 plus. Previously it was 3 plus and then it became 2 plus. Now the value for this type of uh, ligand. Now we should know the value K step value for this complex is 1. It is 1 here. And the value for the K step of this complex, it is basically 2.40 into 10 to the power 5. 2.40 into 10 to the power 5. So now we have constructed an equation here. The equation between this with the Kf to make the compound. Now this is a complex which is formed here. Now after that, they are saying that if we add now a few drops of KSCN means that we are going to add KCN into this complex, which is the product of the first equation. I can write it as equation 1. Now for equation 2, I will use the same complex as a reactant. Now this is now the reactant of the which was previously the product of the first equation. Now if we add KSC and ligand or the compound into it, then it will lead to the formation of this ligand and it will replace fluoride. Why is that so? Because fluoride has less stability here. We have the formation of SCN is more. It is considering about the exchange of the ligand, not the stability of the complex. So it will form Fe H2O with 5 ligands and then SC and thiocyanate ligand. Now it will be similar to the same complex present in this table with 2 plus charge on it. All right, now the 2 plus charge. Now the value for the original complex was 2 into 10 to the power 2.4 to the power 5. And for this ligand, the value can be taken from the table, which is 1.40 into 10 to the power 2. 1.40 into 10 to the power 2. Now you can check here that previously we added the Kf into that complex which had only a value of 1 and it led to the formation of 2.40 to the power 5, which means the K step value of this compound, I'm just to make it feasible, I'm going to label them as A, B, C. This complex is considered as A, this complex is a B, this is also the B, and this one is a C complex. Now we can clearly say that the value for K step of complex B is much greater as compared to K step value of A. So if the concentration of B is much higher than the or you can say the stability of B is much higher than the stability of A, then it means that B will be preferably produced as compared to the complex A. Now, they said that after the equation 1, we had the equation 2, or you can say the next experiment, in which the initial product of first equation was reacted with KCN to produce another complex C. But we can see the value of the C complex is smaller than K star value of A. So, K star of C is smaller than K star of A. It means that C will not be preferably produced as compared to A. So the only complex that will remain in the mixture will remain complex A, which is, sorry, not the A. Small mistake here. The K stab of B was higher than the K stab of A, and the K stab of C was smaller than the K stab of B. In both cases, the complex B will be preferably produced as compared to both complexes A and C, because B has the highest value. We can also consider, I can also write in terms of the values 2.40 into 10 to the power 5 is greater than 1, and 2.40 into 10 to the power 5 is greater than 1.40 into 10 to the power 2. Now, in terms of the observations which they were asking, describe any observation, then we have to consider the colors. So the one, this is the complex A. I have given this complex as A, and this one as B, and this one as C. Now A has a violet color. So I can say this is a violet color, and the complex B, all right. This is not complex B, it is this is complex B in my words, which in here is B. So this is B and this is C. Now the color of complex B is colorless. So complex B is a colorless. And then complex C is FCN complex, which is red in color. So this is red. So what we observed here, that when we added the KF, then the color of B was produced, which was colorless here. Colorless complex are produced from the complex A, which was initially violet color, and when we added the KCN into it, then the complex C was not produced because its value was smaller. So case tab C, the complex C was not produced, which means that the color of the complex B remained as such. It didn't change. It remained as such, and the complex B had a colorless color. It was colorless. Now that's what we have designed from here. Now we have to put all this information into the paragraph form, and we have to also give the explanation. So now coming to the question here, we have to apply all the information here, what we have designed, what we have inferred from here. So in terms of the description, we can say that a solution turned from violet, or you can also call it as purple, to colorless. Why it happened? Because there was the formation of the complex B from A. A was violet color complex and B was colorless complex. That's why. And after that, when you added the KCN, it did not produce the complex C, which means the colorless color remains same. It didn't change. So I'll write and solution then remain colorless, or then remain colorless, or there was no change in color because we did not get the complex C. Now we have to explain the reason. We can say that the K step, now you do not need to write A or B or C here. You need to write proper name of the complex because the K step of, now we know the value of highest value is here, which goes to 5 water ligands and one fluoride. K step of Fe 5 water ligands and fluoride complex having a charge of 2 plus is greater than the K step of the initial complex, which we know is having 6 water ligand, which is also mentioned in the question. Fe, this complex, FeH2O6 and 3 plus charge. The reason was that because we got the formation of this complex as compared to this one, and now and also the FeH2O5 F2 plus was also greater than the K step of the C complex. The C complex was basically the one having SCN. K step of Fe, H2O5 and SCN charge of 2 plus, which we got from the table. So that's how we give the now 1 mark will go for the color change. Color change has 1 mark. And explanation has 1 mark. Now the next question is hydrated compound J, which is this compound, contains a green complex, and this is another complex now. The value of X can be determined by titration of sample of J with SMnO4 and MnO4 minus ions oxidize the C2O4 minus, which is oxalate ions. Write half equation for oxidation. Now we have to write the oxidation of the C2O4 minus 2. Now it can be seen here that we will apply the oxidation reaction of C2O4 minus 2 simply. C2O4 2 minus will undergo the oxidation, and we can see from this equation that we have the formation of carbon dioxide and water. So these are only products obtained from the organic compound. So carbon dioxide will be produced along with the formation of the water, and no, not the water here, because water will come from only from the hydrogen ion, which is basically linked with the MnO4, since it said acidified MnO4 minus. So whenever we will apply MnO4 in the next equation, we have to add the hydrogen ions, but not in the case of oxalate ions. Okay, the only product obtained is carbon dioxide, but since it is the oxidation reaction, we have to include the electrons on the product side. But since the charge is not balanced, we have to minus on the reactant side and only 1 electron on the product side. So we will write 2 electrons on the product side. Now check the number of atoms of the elements. Since it is C2, so I have to write 2 over here to make it balanced. So 2 carbons are balanced and also the oxygen atoms are balanced. Now this is the final answer of this oxidation. Now about the reduction of MnO4 manganate ion. So manganate ion must be reduced, which means I have to add electrons here, but in the presence of the hydrogen ions, because it said acidified, so plus hydrogen ions. All right, now along with that, electrons are added. So what shall be the product here? The product can be seen from here. It is Mn plus 2. It is a reduced form. Along with that, we have the hydrogen and oxygen, so we would also get water here. Now these are the products. Now balance the equation. According to here, we have the 4 oxygen atoms here in MnO4, so I will write 4 here. Now oxygen atoms are balanced, but the hydrogens are atoms have to balance, so we have 8 hydrogens on the right, so 8 hydrogens on the left. Mn is already balanced, hydrogen are balanced, and oxygen are balanced. Now check the charges. On the left side, the charges are -1 from here, -1 from here, and +8. So -1, and +8. It will give me +6, and on the right side, it is +2, and 0 charge on the water. So it is not balanced. So to make it balanced, I have to uh, reduce the +6 to +2, which means in that case, I will not change the value of hydrogen ions. I will simply add electrons here because we already know that the Mn state was changed from +7 from here to +2, which means there was a loss of 5 electrons. You can see uh, reduction in the oxidation state by a value of 5, which means 5 electrons were lost. Or sorry, 5 electrons were gained because it is reduced from +7 to +2. So 5 electrons gained. So that's why I have written 5 electrons here now. As you can see, the charges will now be balanced because in now this time it will be -1 and -5 for 5 electrons and +8. Now it will be equal to, I have -6 and +8, which is equal to +2. So +2 on the left side of the equation and +2 on the right side of the equation. So that's fulfilled. Now the next question, part 2. A student prepares solution containing 0.1 gram J. The student titrates with 0.02 moles cm3 mole per dm cube KMnO4, titrates 12.2 cm3. Assume all seed ethane diuate ions are oxidized. Calculate value of X. All right, so now here we have to do some complicated calculations, and this is a very important question of this paper. First of all, we will convert the concentration and the volume of potassium manganate into the moles. This is C and this is V. So the number of moles of potassium manganate KMnO4 will be equal to 0.02 into 12.20 divided by 1000. Since the volume is in cm3, so we divide by 1000. Now the value will come out to be 2.44 into 10 to the power -4. 2.44 into 10 raised to the power -4 mole. All right, now this is the value for the moles of potassium manganate. Now the question is saying that the reaction is between potassium manganate and the ethane diuate ions. which means we have to consider this equation now. We have just calculated the number of moles of potassium manganate and it was reacted with a C2O4 minus ethane diuate. And we are supposed to find the value of X in the complex. For this purpose, we must know how many moles are there of ethane diuate ions. Only then we can compute the mass of the compound, and from there we'll find the mass of the we'll find the value of X. So the value of ethane diuate ions can be calculated if we use this stoichiometric equation in which we have 2 moles of potassium manganate and 5 moles of ethane diuate ions. So I'm going to take the ratio between the I have the ratio between the MnO4 minus ratio C2O4 minus 2. So we have 2 ratio 5 over here, 2 ratio 5 here. Now the value of manganate, potassium manganate is already calculated, which is 2.44 into 10 to the power minus 4. And the value of ethane diode is to be calculated, which is now X. So when you do the cross multiplication, the X will now be equal to 2.44 into 10 to the power minus 4 times 5 divided by 2. Now this value comes out to be 6.1 into 10 to the power minus 4 mole. X is this, so which means that the number of moles of C2O4 minus 2 is 6.1 into 10 raised to power minus 4 mole. Okay, so we have just calculated the number of moles of this part only. Now we have to consider one more relationship between the moles of the C2O4 along with the moles of this whole complex. Now what do you see here? We can see that K3 Fe complex having C2O4 ratio X H2O, it contains 3 moles of C2O4. That's what we observe here. We have 3 moles of this we have 3 moles of ethane diode within this complex. So we are now going to take the ratio between them. We see that if there is 1 mole of this, then there are 3 moles of the ethane diode. And the one which we have calculated here was 6.1 into 10 minus 4 for the ethane diode. So 6.1 into 10 to the power minus 4 mole for ethane diode. So at this case, the value for moles of this whole complex will be X. So now, if you calculate X now, X will now simply be 6.1 into 10 to the power minus 4 divided by 3. This time, the value will be equal to 2.03 into 10 to the power minus 4 mole. Now, this value belongs to the moles of this whole complex. K3 Fe C2O4 3.XH2O. In other words, I can also write it as number of moles of J since this compound is symbolized as J. Okay, now I have calculated the number of moles for this compound J, which is 2.03 into 10 minus 4. Now, I am provided the value of the mass of J, which is 0.1 gram, and I have got the value of moles. So I will use simple formula, N is equal to mass over MR for the compound J. So mole of J is equal to mass over MR. So from here, we calculate the value of MR, which will now become mass over mole. Mass is 0.1 and the mole is 2.03 into 10 raised to power 4. So after doing the calculation, it will be 492.61 gram. Now this is the mass of this whole compound. This whole complex has this mass. All right. Now I have to subtract the mass of this portion from the whole complex mass. I can use the mass of this part, and I will subtract the mass of this part from the 492.61. So what is the mass of this portion now? Simple. For potassium, it is 339.1 times 3 plus for iron, the mass is 55.8. We can use the periodic table. Plus, we know the carbon is 12. For 2 carbon is 24. And oxygen is 16 times 4. And then multiply this with 3 because we had 3 ethane diol. So when you compute this value, you will get the answer 437.1 gram. Now I have got these two values. This is the value without the water, and this is the value including the water. Simple. Now the next calculation is, or in other words, I can say hydrated, which is compound J, having a water molecule bonded minus anhydrous. This will give me the mass of the water. So hydrated mass is 492.61 and anhydrous mass is 437.1. Now the value will come out to be 54.91. Now this is the mass of the water. Okay, now next part is simple, divided with its relative mass, its MR value. So 54.91 divided by the MR of H2O, which means 54.91 divided by 18. So when you calculate it, you will get the answer 3. So 3 is the final answer. Now, next question is based on question number 4, part A. State the difference in basicity of ammonia, propylamine, and propylamine. So your answer. All right, so for this question, we need to go into the literature, what we know about the basicity concept and how that basicity is associated with these 3 types of the function groups. So I'm going to show you my notes, and in my notes, you can find these topics about the basicity of ammonia, amines, and amides. So within the amine, we have further 2 types, the alkylamines and the phenylamines. So basicity is basically the ability as a proton acceptor for the bases, how easily they can accept the protons. If they readily accept the proton, then they become a good basis. So it is associated with the presence of the lone pair of electrons to form the coordinate or the dative bond with the proton. So basically, the electron pair which are present on the nitrogen atom, they have to do with the making dative bond or coordinate bond with the protons, so they become a good basis. So we have the alkyne amine over here reacting with the water to make the this type of the this type of the acid. This is the conjugate acid of the amine, alkylamine. Now we know that the order of the acceptance of the alkylamine versus ammonia. We will not discuss phenylamine since it is not what it is inquired in the question. We have to do with ammonia and alkylamine. So why ammonia is less basic than alkylamine? It is because the alkylamine contains a alkyl group, which is acting as a positively inductive effect or electron releasing group. So they donate the electron towards the amine group of the alkylamine, and so more electronic charge is present on the nitrogen. So it becomes highly electronegative. So electron density will be drawn towards the high electronegative nitrogen atom, and this causes the nitrogen atom to accept the hydrogen ion to make the coordinate bond with the hydrogen ion. So the basicity of the amine is increased by the ethyl group or any of the alkyl group. And then about the ammonia. The ammonia has a hydrogen atom which is bonded with the NH2 part, because we know that ammonia is basically hydrogen bonded with NH2 to make NH3 ammonia. So the hydrogen atom is basically does not contain any of the electron releasing group or electron withdrawing group. It does not have any of these two groups. So basically it is less basic as compared to the alkylamine. So we will look only these two orders right now. So this is how we associate them. Now the next part will be the basicity of amides versus amines. So here we will discuss how the amides are compared with the amine. Now, in case of amide, amides are very weak bases. The reason is that uh, the lone pair of the electrons on the nitrogen atom is involved in the resonance structure or delocalization. Resonance means delocalization. What it means that the electrons on the nitrogen atom are also involved in delocalizing on the other highly electronegative oxygen atom, and like electron pairs, the negative charge of the nitrogen goes on the oxygen to make it negative part. So basically, the electron is intermediate. It is considered like moving over the NCO group. This NCO group contains the negative charge on it. So the lone pair of the electrons are delocalized over the NCO group or into the CO group. We can also say it as a CO group as well. So that's the reason that this delocalization makes it more stable part. So the stability arises because of this delocalization of the electron. This helps to explain the lower basicity as compared to the amines. Why? The lone pair of electrons is much less available to bond with the hydrogen ion. And a positive on the nitrogen atom would also repel a positive charge hydrogen. So this positive charge is also repelling the incoming hydrogen ion. So that's why we say that it is less stable, it is less basic as compared to the amine. So amine has had the alkyl donating group, a positive inductive effect, whereas the amide has does not have the electron donating group. On the other hand, it is because of the delocalization of the electrons. Now we'll write down the answer in our question. First, we need to tell the relative order. So the relative order is with the weakest base will go to the ethane amide over here. So I will write the name of the compound, propane amide. Just one more thing. If any of you want to get these notes, they can request me on my WhatsApp number or my comment section and on the email address as well. I can give you the access to these notes. So propanamide, and then comes the ammonia, and the strongest one was the propylamine. Now I will write the reasons. Basically, basicity is linked to p orbital of nitrogen atom or lone pair of electrons. Lone pair of electrons on nitrogen, and it is also associated with the acceptance and accepting hydrogen ion, or you can say the donating lone pair of electron to hydrogen ion. So these are associated with the basicity. Then about the reason behind the propylamide to be weakest base is that propylamide propylamide has a lone pair uh, or the p orbital of nitrogen atom, which is being delocalized uh, onto carbonyl group, or you can say over the NCO group, or you can also say across the two electronegative oxygen and nitrogen groups, nitrogen atoms. And for the propylamine, you can write for propylamine, or you have the alkyl group, or you can say propyl group, and it is electron donating group, or it has a positive inductive effect. So that's how you can write the answer. You can have a clear idea about the same question by looking into these mark schemes from different papers. One paper had 4 marks, but I have omitted a mark 1 because it was associated with the order of the alkyl amine, ammonia, and amide. So the reason behind the basicity has these points in this question, and similarly, the point behind the basicity for another paper is having the same words almost. Then second part, so second mark, next mark is associated with the explanation for the alkyl amine over here in this part, and similarly, reason behind the basicity of alkyl amine over here. And then the reason behind the weaker basicity of amide is mentioned here, and similarly, reason behind the weaker basicity of alkyl amide, and you can say the amide compound is mentioned similarly in this paper. So you can write these points in your answer as well. Now the next question. Figure 4.1 shows 2 different ways to synthesize propylamine. So we have the formation of propylamine over here. now we have to see two different routes here and identify compounds K, L, N, K, L, M, region M. So K is reacting with ammonia to make the we have the propylamide over here. So propylamide formation by reaction of ammonia. Okay, so for this purpose, I will show you my notes. Here are my notes in which we discuss the reactions of acyl chlorides to produce esters and amides. And within that, we have the reaction with ammonia and amines. So this is where the acyl chloride reacts with the ammonia to make the amide compound. So this is similar compound is mentioned in our question. We have to produce a propylamide here. So instead of the ethyl chloride, we will write the propyl chloride in our question. So propyl chloride, CH3, CH2, and then COCl. So this is propanol chloride. So propanol chloride with ammonia to make this propanamide. Now the next is the identification of compound L. Now this is the reaction of bromoethane with KCN in the presence of ethanol to make compound L. Now it is basically taken from the AS chemistry. And again, I will show you my note where we learned the reaction between the halogen alkane compound with the cyanide compound. So in the presence of halogen alkane compound with cyanide, we get the formation of the nitrile here. So a nitrile compound is produced in this case in the presence of the KCN and ethanol. So here we will write similar result. We will now have the but this time there are since 3 carbon atoms to be formed here. I will write L as the propane nitrile, not the ethane nitrile. It will be propane nitrile, CH3, CH2, and then CN, which is basically the propane nitrile. So, okay, now this is formed here. Now about the M. M is the one which is converting this propane nitrile into the amine compound. So we have to look the literature of this conversion. Now that comes again in this knowledge. And we have here, again in my notes, you can see that this is the acyl chloride compound over here. And this acyl chloride compound is converting into the amine at a later stage. Or in other words, the amide is converted into the amine compound. This is what we have to find. The conversion of the, here we have to consider conversion of the nitrile into the amine compound. All right. All right. So here, the actual answer was present here. We have to get the amine compound from the cyanide. So for this purpose, the reagents used could be either lithium tetrahydroaluminate 3, is lithium aluminum hydride, the second name of the same reagent, or you can also use the hydrogen over nickel catalyst. So both of these reagents are basically possible to be used here. Hydrogen along with the nickel catalyst to convert this cyanide ion into the amine compound. So this is our answer over here. LiAlH4, or you can also use H2 plus nickel catalyst. Now the next question Question number the C part. Compound N is shown. Compound N is treated with excess of HCl and undergoes complete hydrolysis to form three products. So the products are isolated from the mixture at pH 4. Draw the structures. All right, now here the reaction is between the compound N and the concentrated HCl. Now what do we see here? We see that in the compound N we have the amide group present here and another amide group present here. And it says that assume that CH3O does not react. So this will not be reacting with the HCl. So the reaction is between the amide with the HCl. Now I have to show you the literature. What happens when there is a reaction between an excess of the HCl with the amide compound. So for this purpose, I'll show you my notes here. It says that when the compound is amide and it goes hydrolysis with the acid, then what happens? We see that there is a formation of the carboxylic acid over here, and there's also the formation of the primary amine compound. But this primary amine compound will react with excess acid to make its ammonium salt like this. So the R2 part of the amide becomes the ammonium salt or ammonium ion in other words. So this happens when there is a reaction between the amide with the excess of acid. Now we apply this concept in our question, and we have to discuss the product at pH 4, which is the acidic media. So formation of salt will not be there. Instead, there will be the formation of the protonated ammonia or amine. So we'll discuss the protonated amine here because there will be an excess of the hydrogen ions in the acidic media. The protonated amines will be shown in the structure. Now, first we'll discuss how this compound will be split into its substituent parts by reaction with the HCl. Now we see here, if I make it closer, if it is the compound and the HCl is attacking on this compound, then you know that this is the amine part or this is the whole amide part. But this amide part will be split into two. And as a result, this side will become the amine part. This side will become the amine part, and this side will become the carboxylic group. So this is one splitting. So I have one fragment over here, and another fragment will be here, but it is also linked with the amine group on the other end. So I can say this is broken from here. So this part will become amine group on this side. Now, this is the second fragment, and this is the third fragment in which it is the COOH group on this side and an entire group on this side. Now I have got three fragments which I will get here. I can write the third fragment in a simple way. Third is the CH3 COOH. It is the ethanoic acid. So ethanoic acid is formed here. And then about the first fragment, it is simple. I have the benzene ring. It will be connected with the one compound carbon molecule here and then bonded with the amine. But we should consider that it should be protonated. So it should be written like this, NH3 with plus charge on it. If it was producing salt, then we could write like this. But since pH value is equal to 4, which is an acidic media, so I will need to remove this chloride part from here, and it will become this point, this part. So this is my another fragment, and the second one will be shown in the box mentioned below. So I'm going to draw the second fragment first to make it easier. So this side will have the carboxylic acid. So I'm going to draw the carboxylic acid like this, HC double HO H-double-O-C. So this is my C carbon of this side. This is my C, and that C is bonded with this portion. This part is bonded with the carbon. So CH, this CH bonded with the CH3O like this. And then the next part was again amine part. So it should be protonated amine. So NH3 positive like this. So this is my compound over here. It should be learned here that this oxygen was basically connected with a carbon. So I will write oxygen, and like this I have CH3O like this, because oxygen is in between these two carbon chains. So this is my second fragment, which I labeled here, second fragment or second constituent. So now we just need to draw the remaining two parts. I can write first part over here. So it's benzene ring, and one carbon over here, and then protonated amine. And the third one was the ethanoic acid, which is simple, CH3 and COOH. So this is my third fragment. So that's how the answer is completed now. Now the next question, the compound P can be synthesized from 1-methyl-4-nitrobenzene by the route shown. So we have this route by which this compound is formed. Step 1 is the reduction reaction. Complete the equation for this reaction. Use hydrogen, this K bracket hydrogen to represent an atom of hydrogen from the reducing agent. And we are given the molecular formula of the reactant, this reactant, which goes through step 1 to make this compound. All right, so for this purpose, the simple way is to write a similar molecular formula over here to make it easier for you to write the equation. So C7H7 and NO2, that belongs to this compound, and it goes to this compound which has a molecular formula C7H7, and this part will be written later on NH2 like this. So it reacted with the hydrogen ion coming from the reducing agent like this, and then it converted into this amine compound. Now, what you need to do is to balance the elements as well. And the product form in this case will be oxygen removed from here that must be reacted with the hydrogen to make water. So water must be done here. All right, now balance the elements. Since the oxygen atoms are 2 here, so I will write 2 here. Now that gives me 4 hydrogen atoms and 2 over here. So in total, I have 6 hydrogen atoms, which are additional as compared to the reactants. So I will write 6. So this will become my equation. So you just have to write 6 hydrogen like this, and then C7H7 NH2 plus 2 water molecules. Now the next question in this table, complete the table. So it says you have to complete these 4 steps. The first step says reagents and conditions required, and the type of reaction is reduction. Now, first step included conversion of nitro group into the amine group. So we need to see which reaction conditions are required for conversion for reducing the nitro group into amine group. You can see this topic in my notes. Preparation of phenylamine, and here we have the conversion of nitrophenyl nitrophenyl group into the phenylamine, and for this purpose you will need a tin compound, tin aluminum, along with a concentrated HCl with heat. So heat plus HCl plus tin is required. Similarly, the same topic is mentioned over here, in which you can see this nitrophenyl is converted into phenylamine using the 10 plus concentrated HCl and heat. So you will simply write these reagents and conditions. Sn plus Sn and concentrated HCl is reagents and also heat. Then second step. So second step, we have to explain the type of the reaction as well for the second step. Now second step says it can go from phenylamine into this compound, which is a disubstituted amine compound. It is a disubstituted, it is not monosubstituted, it is a disubstituted amine compound, which is similar to ammonia being converted into similar compound of ammonia having two alkyl groups bonded with it. So it is similar that two hydrogen atoms are replaced with two alkyl groups. So you can write it like this, NH and R2, converted from ammonia to this compound. So where can we find this type of reaction? For this purpose, I will show you notes. One part is coming from the AS chemistry, and this is a page from AS chemistry in which you learn that when halogen alkane compound reacts with ammonia, it forms the amine compound. Now, what do you see here? That the initial haloalkane compound had bromine bonded with the alkyl group, but then alkyl group is bonded with the NH2, which means there is some sort of the substitution reaction in which the nucleophile has been substituted. The bromine was with the alkyl group, but then the alkyl group is with NH2. Now this reaction can carry on, and you can see this type of the reaction even in the amide compounds. Here this is the substituted amide. In a similar way, the amide compound, which is a derivative of the halogen alkane, reacts with the amine compound, and you can see that now this time the nitrogen previously the nitrogen had two hydrogen atoms, but now nitrogen has two alkyl groups. This is one alkyl group and this is another alkyl group along with one hydrogen atom. So which means one alkyl group is now converted into two alkyl groups, R1 and R2, which can carry it forward with a similar type of the amide acyl chloride compound, and this time the nitrogen is bonded with three alkyl groups. Now the same concept can be applied for the amine compounds, in which our case in the question, when we see here that the nitrogen was previously bonded with only one alkyl group, but then it was converted with it was connected with three alkyl groups, two alkyl groups over here and one alkyl group over here. So we can see that it is some sort of a nucleophilic substitution for which uh, the amine is bonded with the alkyl groups more. So here, which kind of the halogen alkane compound is required? It must have the CH3 group, and that must be bonded with any of the halogen elements. It can be chloride, it can be bromide, it could be iodide. And these reactions are being carried out in the presence of the ethanol, which you can see here, where this reaction was carried out in ethanol. So you have to write the ethanol as well. And the reaction type is the nucleophilic substitution reaction. This is a part of the nucleophilic substitution reaction. Okay, now we give the answer like this in the table form, that this is reacting with either CH3, Cl in the presence of ethanol, and the type of the reaction is nucleophilic substitution. Nucleophilic nucleophilic substitution reaction. Or you just can write only the substitution reaction that could answer to the correct answer. Now step 3. The step 3 over here is the conversion of alkyl group into the carboxylic group. That is clearly seen as the oxidation reaction here. So oxidation of alkyl group into the carboxylic acid. For this purpose, we remember that we use the hot KMnO4. We use hot KMnO4 that show the oxidation reaction. Oxidation reaction. And then the fourth step, it says condensation reaction. Now in fourth step, we can see that there is a conversion from carboxylic acid into the ester, which means this is ester compound, which means it is a esterification reaction, or you can also call it as condensation reaction. Now we remember that for the formation of ester, we require carboxylic acid plus alcohol. So the reaction is between these two compounds in the presence of the acid, which is an hydrolysis reaction. So which alcohol should we use here? For this purpose, if you look at the structure of the acid, we can see that this oxygen bonded through a single bond is basically the one which comes from the alcohol group. So this should be the compound which must be the or alcohol. It would be this compound. So simple, we just need to draw the structure here of the compound. We don't need to draw in molecular form or in displayed form. That is fine if you just draw the skeletal formula. And it happens in the presence of the acid. Now the question number 5. Cumene is an aromatic hydrocarbon used in synthesis of other useful chemicals. This is the structure of cumene. Complete the table to show the number of sp2 and sp3 hybridized carbon atoms that are present in the molecule. All right, so here we need to find which carbon atom shows the sp2 and the sp3 hybridization. Over here, we can see that this part is basically the part of the phenyl compound in which we know that the carbon atoms have the alternating double bonds. And these double bonded carbon atoms are basically those which have the sp2 hybridization, which we learned from AS chemistry. So all these 6 carbon atoms, 1, 2, 3, 4, 5, 6, they all have the sp2 hybridization. So the number we will write number of carbon atom to be 6 here. Now sp3, we know sp3 only happens when carbon is bonded with 4 different, we know it should be bonded with 4 different groups. Or it is, you can say it is a tetrahedral shape. So this can be seen here. One carbon atom here, another carbon atom here, and another carbon atom here. So we have 3 carbon atoms which are sp3 hybridized. Now part B, cumene can be synthesized by Friedel-Crafts alkylation reaction. So this is the reaction. Name the mechanism involved in this reaction. So we know that Friedel-Crafts alkylation goes through the electrophilic substitution reaction, because we have the formation of electrophile, in this case from the bromine bonding, reacting with the catalyst generator. Now identifies 10 second part. The first step of the reaction from this cation identifies a suitable region for the formation of cation from this 2-bromopropane. So here the halogen carrier must be mentioned here. So the halogen carrier over here is basically the AlBr3, or you could also write FeBr3. Why only Br3? Because we have bromine here. So the halogen carrier must contain bromine. And you could also write it as like this. Anyways. Now the next question, number 3, complete figure 5.3 to show the mechanism for the reaction benzene with this cation. Include our relevant the arrows and charges. So whenever we have a type of this reaction and we have to indicate the mechanism, then we must indicate all the arrows and charges and the breaking of the double bond or lone pair of the benzene and then formation of the presence of the positive charge. So for this purpose, I will show a picture of these stats. You can see here, this is how we have the reaction. The cation reacts with the benzene, and we have cleavage of the lone pair of the benzene, and then the reformation of the double bond and the removal of the hydrogen ion reaction with AlCl4 or another halogen carrier for the reformation of the catalyst, and again reformation of the or the formation of the alkyl group on the benzene. So this is how we represent the mechanism. Now in our case, the reaction is with the CH3 uh, double methyl group with the CH2 positive with the CH positive. So I will need to show the arrow here that this double bond is going to be broken from this point. If it's broken off from this point, it reacts with this part, and this is already a positive charge. So the intermediate will look like this. Now I have broken the double bond from here, which means I need to indicate the remaining 5 carbon atoms like this, and the positive charge should be present in the center like this, and then a hydrogen atom is shown separately over here, and this catalyst, this cation must be bonded on this point to the carbon atom like this. Okay, so I have now shown like it like this. Now I have to show that in the next step, this hydrogen will be broken off from here as hydrolytic fission, and this will go into the center like this, because we have seen that a similar type of the arrow must be shown here, that this hydrogen bonds break hydrolytically and arrows go inside the horseshoe type of the lone pair, and we have the formation of the benzene compound again. So it moves back into the here, back into the benzene ring, and then we have the formation of this whole compound along with the formation of the hydrogen ion. So this is how we represent the mechanism of this reaction. All right. Now the next part, the physical alkylation benzene by 1-propene also produces cumene as a major product. This compound cation from the first type quickly rearranges to this. It's just fine. All right. Now it says that if there is another reaction in which we use 1-propane, then it should form this cation. But this cation is converted into this cation. Why is that so? Why it happens? We can see that in case of this initial compound, the positive charged carbon, which is called carbocation, had only one alkyl group. This is the alkyl group CH3, CH2 bonded with this, which we mean as primary carbocation. It is a primary carbocation over here, in which only one alkyl group is bonded with a carbocation. Whereas in this case, we have the carbocation over here bonded with two alkyl groups. So this is the secondary carbocation. So we know that secondary carbocation is more stable than the primary carbocation. So I can write it as that the CH3 whole twice CH positive is more stable. It is more stable due to greater positive inductive effect. Positive inductive effect of alkyls. That's why. So carbocation is more stable than the primary carbocation. Now the next question, C part, cumene oxidizes in air to form phenol and propylamine. Fraction 1 is given with delta S value. So then we have this table. Table shows the standard entropy values for these compounds and the elements. Calculate the standard entropy change delta S naught of reaction 1. So we have the delta S value. We have the standard entropy values for all four substances. Now we need to apply the formula that uh, standard entropy change represented by this is equal to standard entropy values of the products, sum of the products minus standard entropy, sum of the standard entropy values of the reactants. So product minus reactant is a simple formula which we have to apply here. Now, the product values are given here. These are the products and these are the reactants. So simple apply, use these values. So products would have C6H5OH, which is 278 plus propylene. Propylene value is 200 minus there is a slight mistake, not 278. It is basically this is products phenol, and phenol value is 146. So 146 plus 200, and then minus from the reactant values. This compound, it has a value of 278, and you can also minus similarly the another reactant, second is O2, its value is 205. So when you do the calculation, you will get the answer as minus 137. So one less 137 is the final answer. Now the next part show that reaction 1 is feasible at 25 degrees centigrade. Okay, so feasibility means we have to check the spontaneity of the reaction, which is related with the Gibbs free energy represented by delta G, which means we are supposed to find that delta G is to be calculated, which must have a sign of negative. So it says show direction 1 is feasible, which means the answer should come to be delta G having a negative answer. All right, now what's the formula of delta G? Delta G, when related with the delta S entropy and enthalpy, was enthalpy value is given over here, and we calculate the entropy value over here, which we can now link with the formula delta G is equal to delta H minus T delta S. Now that's the formula which we are going to apply here. Okay, so delta H is already provided, but T is the absolute temperature, and we have to calculate the value in Kelvin. Absolute temperature already calculated in Kelvin, so convert this centigrade into the Kelvin. So it will be 25 plus 273. So this will give you 298 Kelvin. So absolute temperature is calculated here. And then one more thing. The delta S was previously calculated in joule. We have to convert the joule into kilojoule. That's a requirement because delta G and delta H, they both are given in kilojoule. So that's why we have to convert joule into kilojoule. For this purpose, this minus 137 will be divided by 1000. So this will give you minus 0.137 kilojoule. Okay, now we substitute the values here. Delta H value was given in table, and this equation minus 371. Delta H is minus 371, then minus T is calculated to be 298, and then multiply by delta S is calculated to be minus 0.137. 137. Now, when you compute this value, the answer will come out to be minus 330 kilojoule per mole. Now, you can see that in this answer, the negative sign is there. That indicates that it is a feasible reaction because the value of delta G is negative. Now, the next question, number D, figure 5.4 shows two reactions of phenol. This is the reaction of phenol with Br2 in reaction 2, R and NO in reaction 3. State the condition for the bromination phenol in reaction 2. Explain why this condition different from those for the bromination benzene. Okay, so here we have to discuss the conditions for phenol reacting with the bromine. For this purpose, I will show you the notes in which all the conditions are mentioned. Okay, so here in my notes, you can find that phenol reacts with aqueous bromine, or you can say the bromine water. You can either write the bromine water with which it reacts, or you can also write aqueous bromine. Both are fine, and they react without a halogen carrier here. We know the halogen carrier is basically used in case of the benzene compound like AlBr3 or AlCl3 whatsoever, but here it is the bromine. And this can react even at room temperature, whereas benzene does not react at room temperature. Uh, it does react more stronger conditions. So there's a difference here. We will now write over here that the conditions required is basically the aqueous bromine, or you can write bromine water and no halogen carrier required, or the halogen carrier could be written as AlBr3. So these are not required here. Explanation why their conditions are different as compared to the conditions of benzene. Now, benzene is similar, is just like this. It is simply a hydrocarbon. So it is not halogen compound. It is only this compound, benzene. So why that so? The reason is that within the benzene compound, we have the lone pair of electrons. The lone pair of electrons or the p orbitals on oxygen at on the in case of the phenol, we have to decide about the phenol first. The lone pair of electrons on the oxygen atom in phenol overlaps. You can say that it overlaps, or you can say delocalizes with the pi bond or pi ring system. That's the reason that it gives delocalization phenomena here, which makes it more stable. Now, in case of that basically increases electron density in ring increases in case of phenol. So if phenol has high electron density in ring increases, or you can say more electron rich system. With more electron rich, it becomes more electron rich, and so it attracts electrify strongly. So this is all happening in phenol. So this causes phenol polarizes the Br2 molecule more. So we have more polarization in this case. So that's why phenol is considered to be showing milder conditions as compared to the benzene. There is no such phenomena in case of the benzene as compared to the phenol. Now the next question, part 2, draw the structure of organic compound Q in figure 5.4. Okay, so we have the draw the structure of compound Q here. Since we can find similar answer from the notes, we had that when three molecules of bromine are reacting with the phenol, we are getting three substituted bromine atoms. We have 2, 4, 6 tribromophenol formed here. So that's how we get the similar result here. You will need to draw structure similar to the question. So she's present here, and 2, 4, 6 means one bromine should be here, another bromine should be here, and then another bromine over here, along with the ring inside. Now the next question, part 3, identify organic reagent R. Okay, now what is R here? We can see that this phenol is basically converted into S, which is an azo dye. Azo dye is formed here, so which means this must contain some sort of the diazonium chloride salt, benzene diazonium, and this part is coming from that R. So benzene diazonium chloride must be there. The structure of that should be having one benzene ring, only one benzene ring here. And then it must have the nitrogen triple bonded nitrogen. You can write a structure like this, or you can also write it like this, having a positive charge. So this is the R compound here. So I'm going to identify organic compound here. So nitrogen is triple bonded with N with plus charge, or it is like this. Nitrogen having a plus charge on it. It is a benzene diazonium chloride. Because we had the OH part over here, which is coming from this phenol. So that's why the whole of this part is coming from the benzene diazonium salt. Now, name the functional group that is from reaction 3. So we just said that the compound form was azodie, which means the functional group is the azo. Now, the next question, the reaction of phenol with nitric acid produces a mixture of isomers with molecular formula C6H5NO3. Identify two isomers that are formed in the largest quantities. Okay, so it says that reaction is between the phenol. So phenol, this is not O, this is basically the ring of the electrons. So this phenol is reacting with the nitric acid, and we know that when this reaction occurred, there is a substitution of nitro group on the phenol compound. So NO could be placed over here, it could be placed over here, or it could be placed over here because it is a 2,4,6 direct input. So I need to show only two isomers. That means these two are similar and these two are different from this one, which means I just need to draw only two isomers here. So first of all, I will draw this structure. This is OH over here and one NO group over here, and then another isomer OH and then NO on the opposite side. So these two are two different isomers. Now the explanation why I am getting these two isomers. The reason is that the phenol or the hydroxyl group OH or the hydroxyl group is electron donating group and also 2,4 directing group. That's why I got nitro groups at position number 4 and position number 2 over here. Now the question number 6, malic anhydride is an unsaturated cyclic compound used in the formation of several polymers. Malic anhydride can be used for malic acid and tartaric acid. Malic acid reacts with ethane 1,2-diol to form condensation polymer. Cross section of this polymer showing only one repeat unit. The new functional group should be shown fully displayed. Okay, so here we have to react this malic acid with the ethane 1,2-diol to form the condensation polymer. Now, how does this ethane 1,2-diol look like? It has CH2, CH2, and one OH group on one side and another OH group on the other side. And this must be reacting with this malic acid. So we have to put in the polymer in which at least one repeat unit is there. So first of all, I'm going to represent the actual compounds, which are represented like this. So this is malic acid here. It reacts with the ethane 1,2-diol like this. Now we know that the reaction is between the OH group of the acid and the hydrogen part of the alcohol. So this must give you the water liberated from here and then the linking of this carbon with the O. Okay, so what do I have here is that I'm going to show the carbon over here, which is bonded with the oxygen like this. And then I can show a structure like this, double bond, and this carbon is similarly bonded with the oxygen through double bond. Now this OH is now removed here because it was used in condensation. Now this carbon is bonded directly with this oxygen of the alcohol. So I'm going to link this carbon since it has shown fully. So I'm going to show this part completely like this. So this O is coming from the alcohol, and then I have the CH2. I can instead show it in the form of the skeletal formula like this. So one carbon, another carbon, and then oxygen of the other part of this side. So this is oxygen over here. Now, I do know that this OH of the carboxylic acid must also be removed because it is used in condensation. So that's the part which I'm going to show like this, because I need to show only one oxygen over here. And then the oxygen of the alcohol is also similarly bonded with the carbon chain of the acid. So I'm going to put curly arrow over here. Now this is how I'm going to show the part of the polymer, and it should not be written N because it is not a full polymer. Instead, it's only a one repeat unit. So we do not write N here. So it is completed now with only one repeat unit, and that's all. Now the next part, identify suitable reagent and the condition for reaction 2. So reaction 2 is over here, and it shows that this acid is converted into this compound in which we have now additional two H groups over here, two hydroxy groups over here. and the alkene group is converted into the alcoholic groups. This is basically the part from the AS chemistry in which we study the reaction with a cold KMnO4. Cold potassium magnate was reacted here in the acid condition. So you can write cold acidified dilute KMnO4. Cold acidified dilute KMnO4. You need to write each and every part here. We need to write cold, acidified, dilute, and KMnO4. Only then you will get 1 mark for this reaction. And then the next part, compound you can be formed from tartaric acid in 2 steps, as shown here. Tartaric acid reacts with this propylamine and hydrogen ion to make this compound. So just the type of reaction that occurs step 1. So step 1, we can see here that we have OH over here, OH over here, but here we have this type of the compound. We can clearly see that this part is coming from the propylamine over here. And what else we observed that we should have 3 oxygen atoms, but here we have only 2 oxygen atoms, which means 1 oxygen atom is with more. Also that if we count the number of hydrogen atoms, then these are 1, 2, 3, 6, 9. There are 9 hydrogen atoms represented in reacting and in the arrow. But here we have only 6 hydrogen atoms, 3 plus 3, 6, which means the hydrogen atoms are less here. That indicates that hydrogen's atom and oxygen are removed. That means that water must have been removed from here. So that indicates the type of the reaction is a dehydration reaction, or you can also write it as elimination reaction. Now the next question, explain what is meant by bidentate. You can act as a bidentate ligand. Explain what is meant by a bidentate ligand. All right, so for this is a repeated question for which I can show you multiple answers. These are answers taken from 3 different papers, and you can note down these answers, and all these questions have 2 marks each. Now the next question, complete the 3-dimensional diagram to show both the stereoisomerism, isomers of Cu, bidentate ligand U with 3 bidentate ligands and 4 negative charge. All right, so for this purpose, we are given a simplicity to write to show the bidentate ligand by this symbol. So we know that copper makes a is a octahedral structure. It should make octahedral structure with 3 bidentate ligands. So I'm going to show picture like this. So this should make 6 bonds. This is wedge bonds, and these are strip bonds. Now we need to show 2 stereoisomers, which means these may be the cis trans, in other words. Sorry, it would be the mirror images of each other. Non-superimposable mirror images. So one bidentate ligand like this, and another bidentate ligand like this, and then another bidentate ligand like this. So this gives me one of the isomer. Now I need to draw another stereoisomer. It is a mirror image of that one. Okay, now similarly, it should be the mirror image. So this bond should come over here like this. And then this will go over right side like this. And this will go on the right side. like this. So these are the two mirror images. Then we have to indicate the square bracket and the 4 negative charge on them. So square bracket like this. And a -4 charge on top of it on both the isomers. Now that's completed now. Now the next question number C, that's apart from the analytical chemistry. A student analyzes an aromatic compound X. This is the formula C8H8O3 using NMR spectroscopy. So figure shows the carbon-30 NMR spectrum of compound sample X dissolved in D2. This is the spectrum of NMR. Separate sample X were analyzed using proton NMR spectroscopy gives information from the analysis. This is the table. Identifying a number of different carbon environments present in X. So looking into the molecular formula of the compound, which is C8H8O3, and also the different chemical environments of the carbon, we need to see that NMR spectrum. Here we know that zero value is for the TMS, which is basically very small line, which is not indicated here. But we are left with these discrete lines, which indicate different chemical environments of the carbon. So we just need to count them. That will show that these are the different environments. 1, 2, 3, 4, 5, 6, 7, and 8. So if there are 8 different lines, it means that these are the different chemical environment carbon atoms. So different carbon atoms will be 8 here. The next part explains why X is dissolved in D2 before obtaining its proton NMR spectrum. So D2 means deuterium here, which is the heavy isotope of the deuterium, which is a heavy isotope, which is hydrogen 2 1. Its purpose is that it should use to remove peaks or the signals, peaks or the signals or absorptions from acidic protons or from the OH groups of the compound, the carboxyl groups of the compound, and to identify um, the OH and COOH protons. So basically, D2 helps us to identify which hydrogen atom signals or peaks were there in the compound. That's why we use a deuterium. Since there is a due to proton exchange with D. All right. Now next question. Now the next question, part 3, aromatic compound X gives a yellow precipitate with when it reacts with alkaline I2. Use information in C to suggest a structure for X. Explain your reasoning. Okay, so here we have to articulate a lot of information. First of all, X was that compound which had 8 different chemical environment of carbon atoms. Now it also says that it must react with alkaline I2, which means it must give the positive test with the alkaline A2. And in that case, we do remember from the AS chemistry that it should be the compound which must contain this group. It must have this group over here, or in terms of alcohol, it should be the compound which must have this group. So it should be there, only then it should give you the positive test with alkaline, or you can call it as tri-iodo form test. So we now articulate here. Now the structure, how the structure should look like here. For this purpose, we must understand that in this table, we saw that initially when the solvent was CdCl3, it had provided the number of signals in proton number as 6, but when D2O was added, it provided 4, which means there's a loss of 2 hydrogen atoms, which means that those 2 hydrogen atoms are basically accepted by either the acidic group or the hydroxyl groups. So we can say that 2 acidic groups or 2 hydroxyl groups were there in the compound in the sample. Now, if we look at the molecular formula, we see that it has 3 oxygen atoms, which means we cannot say to have 3 times of the carboxyl group. That will be wrong, which means it could contain 2 times of the hydroxyl groups and 1 of the ketone group. Only then we can get 3 oxygen atoms completed. So it would not have 3 carboxyl groups. Now, what kind of structure comes in our mind? I can show different structures like this. First, we would have the OH group and another OH group, and then we should have the ketone group over here. Now, this methyl ketone. Only this methyl ketone will be able to give you the triiodoform test. Now, this is the part which is giving the triiodomethane test, this one. And if we look deeply, this would give you 8 different chemical environment carbon atoms. This OH will give these different carbon atoms over here. And similarly, we will have different carbon atoms over here because all of these groups are present at different positions from the 6 carbon atoms of the benzene ring, and then 2 carbon atoms over here. These are all different chemical environments. You can have this structure or you could have this structure as well, in which the OH is present one over here and another OH present over here, and then the methyl ketone over here. Another structure which could be formed is that in which the OH can be taken out from here, and instead I can have the OH groups at this position like this. So one OH group over here and another OH group over here. This could also give me the another type of the structure. Or I could have one OH group at this point, but another OH group instead of here, I could have OH group over here. So these are going to give me 4 different structures. So you can draw any of these 4 structures. Now you have to explain the reasoning. First, we will say that the methyl ketone or CH3CO group gives yellow PPT, or you can write CH. This is a triiodoform compound with alkaline I2. And then you need to tell about the OH group. Why do you say they are 2 OH groups? The reason is that because 2 OH groups, because H hydrogen NMR peaks lost in peaks or signals lost in D2O, which I told you before that we had 2 peaks lost in D2O over here. That indicated that we had 2 OH groups present. And then why do we have ketone group here? Although we told that we should have the positive test, but how can we infer from the structure that we have the ketone? For this purpose, we need to use the table of carbon 13 NMR, and this is the ketone group over here, which lies in 190 to 220 chemical shift value. So if we look this value in the graph over here, we have this line. This is basically linking with the ketone group. And so we'll write over here. How are we confirming that we have the ketone group? Because carbon 13 NMR signal with chemical shift value of around 20. We can see from here the chemical shift value is around 20 and 5 because of its position. So chemical shift value around 205, which is the mid of the 190 to 220 chemical shift value. And another peak which we must have here is for the methyl part bonded with the carbonyl group. So how do we have this methyl group, which is with the carbonyl group? For this purpose, you need to see the alkyl group next to the carbonyl group, which has a value of 30 to 65 chemical shift value. So this is the one which is present in the structure, and we can see in the NMR spectrum, the 30 to 65 is this range. This is the one which is between 30 to 65 chemical shift value. So it also proves as the methyl group was there. So methyl next to carbonyl group, because why was it there? Because we had the carbon 13 NMR with the chemical shift value between 30 to 65 ppm. We need to write ppm over here as well. So this is the reason why we had this structure present here. So we have proved the molecular formula, the 8 different chemical environments, the presence of the 2 OH groups, and the presence of the methyl ketone. So that's how we have completed this paper of 5 March 2025, paper 42. I hope I have cleared all the queries about this paper. If you have any further question, you can let me know. And do subscribe my channel and stay tuned for more videos and the next past paper practice. And if you have any, if you want my notes, do let me know. You can reach me out on my WhatsApp number and my email address. Till my next video, take care and Allah Hafiz everyone.